So, something I wanted to talk about was the concept of test time training because it's become pretty popular over the past year or so. And I think it's a very interesting research direction that we should be prioritizing more. If I mean, we already are prioritizing it quite a bit. Um, but I feel like this is kind of a glimpse into the future of how we're going to build better reasoning models. And we've seen that OpenAI, et cetera, have succeeded on this. But I kind of wanted to take a more theoretical viewpoint or standpoint, and kind of present a different understanding of what this might look like. So, just to kind of get started here, um, typically in machine learning, we have two parts or two phases when we create a model. So, here we have the training phase, and then here we have the test slash inference phase. And some models might go through this training phase and then immediately just go into test and inference and never come back. But you might have certain models that they go into training, and once they're done training, they go here into inference, and then every so often, periodically, they'll go back into training to update their data, update their understanding of the world based on how things have changed. So if this data set changes often enough, they'll go back into a period of some kind of fine tuning, and they'll be redeployed. And this is kind of how machine learning models have been, I guess, like the life cycle of machine learning models. So typically here, this would be your deployment for your machine learning model. We're not going to talk too much about deployment. And this is kind of the research side of what's going on. Somewhere after, during and after training, you'll have model evaluations, certain checkpoints where you evaluate your model to make sure that it's working, blah, blah, blah. But really, this is the understanding of what the machine learning model lifecycle looks like. And some people, instead of doing this, periodic update, instead they just train a new model because maybe the problem that you're trying to solve needs you to pre-train a new model every time. So this is kind of the understanding of test time training, and I'm going to try to present two different applications of test time training that I think are quite different, but I think would work really well. And one of them is popular, it's already been done, and one of them is something that's a lot more niche and that I think has a lot of potential going into the future. So the first kind of application of test time training and how we're going to start thinking about test time training is of course for language models. This has been a hot topic over the past, I'd say, 5+ years, and this is most recently where test time training has kind of become popular and shows promise to develop reasoning models. So reasoning, and just make models that are better at certain tasks. So the first thing I'm going to kind of introduce is my thinking, or my understanding of theoretically how this works. So how we're going to think about this is we have a large corpus, which is our data set, and this is going to be some set of points, x1 to xn, and this is going to be in Rn or Rm for some m. This typically, I mean, we're not going to quantify too much or be too rigorous with what exactly this M here is or how big this data set is. But the idea is we have this set of data points in a particular space. And what we're trying to do, and I mean, this is all of machine learning, right? Is you have some set of data points and you kind of want to fit a model to that set of data points. So of course, what we're trying to do here is we want a model to fit this. But more kind of abstractly, this data is distributed in a very complex way when it comes to language in particular, and natural language. And so just kind of a toy example, and really the data is distributed in a much more complicated way than what I'm about to describe. But I think the description I'm going to give kind of gives a more intuitive understanding of how this theory plays out. So how we're going to think about this is our data is kind of distributed in various clusters. So we might have a cluster here, and then a cluster of data here, and with some points in between. And for instance, here you might have a cluster that talks about cats, and you might have a cluster here that talks about physics, and in between you might have Schrodinger's cat, or something silly like that. So this is going to be physics and cats. And really, all of these points, we can think about them lying in some kind of three-dimensional manifold. I mean, they live in, of course, like significantly higher dimensions, but we can only visualize this in up to 3 dimensions. So let's think about these data points being on some 3D manifold. And so perhaps instead of drawing it as points kind of this way, we can think about this more of as a contour map. So each of these points has a certain height. So maybe you have this kind of visualization of it where each of these points have a certain height associated to them, and they form some kind of landscape. Here it might look something like this. Or really, it could look like anything, right? These points might be anywhere. So here we have 0 kind of along this plane here, and then we have these points both below and above this plane. So really what we're trying to do is we're trying to build a model that's able to fit these points the way that we want to within this landscape. And that's really all we're trying to do in machine learning is kind of fit these points with some kind of statistical model. So this would be our machine learning model. Machine. I'm just going to put machine model. Makes sense. So now the problem is that this data set is massive, right? When we pre-train a language model, we're trying to fit the entire landscape of all possible points in our data set, and our data set is massive because we want this model to be able to understand how to talk, and we want it to be able to understand how to express ideas and just get an understanding of natural language to begin with before we start training it on more complicated tasks such as mathematical problem solving or coding or anything of that sort, right? So the kind of first problem here is the data set is huge, and even though we have several millions or billions of data points, and a lot of these kind of clusters here have very high density. So for example, there could be a lot of information about cats. There could be a lot of information about physics. In fact, there could also be a lot of information about everything in between cats and physics. The model's representational capacity is a limitation here. So the data set is huge, but the model representation capacity, and of course all of these all of this information is kind of encoded within the weights of the model itself. So even if we have a model which has billions of weights, it's very hard to come up with a smooth model for our data set, and really capture all of these dense clusters and the intricacies that go into them. So model representation capacity is limited. And I guess one big reason why this is limited is because in this data set, within clusters, we have certain patterns that take place, right? So here we might see, okay, great, this is the cats cluster, this is the physics cluster, but of course, there's a hierarchy here. These are very big abstractions of cats and physics. So within cats and physics, for example, we might have, oh, there's domestic cats versus wild cats versus all sorts of other cats, right? So, and then within physics, of course, you have different areas of physics that can represent their own clusters. So each of these could be various areas of physics. And really, the understanding here becomes incredibly nuanced, and the kinds of patterns that this model has to fit. I mean, on a larger scale, yes, it makes sense. It's able to fit. It's able to fit this data set. Let's see if I have a pointer here. Here, at a large scale, we are able to fit this data set here, but when it comes to understanding nuances within data sets, you're like, okay, we can understand and fit to the data within domestic cats and then wild cats. But then you have subspecies of cats, or for instance, in physics, you might have quantum physics over here, quantum mechanics, and then within quantum mechanics, you have certain theories and certain subfields. How is quantum mechanics or quantum physics used for computing? You have quantum chromodynamics and so on and so forth. So within physics, there's a lot of different subfields, and there's a lot of nuance built within each of these clusters as well. So it's very hard for a model of no matter what size, because we're not just talking about cats and physics, we're talking about the entire corpus of knowledge that humanity has come up with over the past millennia, right? So it's a lot of data, and this representation capacity is just not good enough. And I think Jonas Huboter came up with a nice analogy, or maybe he didn't come up with it, but he was on a podcast where he presented a nice analogy where this can be kind of thought of as resolution, where this model, this machine learning model, has a low resolution understanding of the entire world. It has a low resolution understanding of every single concept, because the more you kind of zoom into this landscape here, the more you zoom into where these points are and how this data is actually distributed, the more refined it gets, the more fine-grained details you need to be able to represent, and models are just struggling to be able to represent that fine-grained detail when they're trained on such general tasks like language understanding. So this is kind of the problem that we want to solve, is how do we make these models, because if we want to start solving unsolved problems, so within physics we want to solve unsolved problems, then we need a nuanced understanding of multiple fields of physics and really understand the nuanced connections between these fields of physics. So we need a very, very high res map of this space here. We need a high res map of this here. And we need a high res map of their interactions with one another, and maybe their interactions with other fields. So maybe we need their interactions with mathematics, which is a closely related field, but has completely different kind of concepts that that are thought of in a completely different way. So for example, in physics, we think of things, we might think of things experimentally, physically, etc., etc. But in mathematics, we might think of things in a more abstract form without thinking of their applications in the real world. And so it's hard, because you need to not only have a high resolution picture of all of these spaces, you also need a high resolution picture of various fields of mathematics, and these models just don't have the capacity for that at the moment, and I don't think scaling these models up is going to solve it. So I guess another comment here is this kind of capacity being limited between I guess 2020 to 2024. Actually, even 2025, our solution has been to scale things. So we just give the model more parameters, and and hope that the representational capacity of this model becomes good enough in order to be able to capture all of these nuances and understand all of these connections. But really, really, scaling is not going to work long term, because the more fine grain detail we need and the more information we gain, the harder it's going to be to just continue scaling these models and expect it to perform the way we want them to. So this is kind of a presentation of the problem that we're trying to solve. And the way that test time training aims to solve this problem is to say, okay, I'm fine with having a low resolution understanding of everything. But the moment I notice that I need to use a higher resolution kind of map or higher resolution model of what I'm trying to understand, I'm going to start training again on a very particular subset of all the data that I have in order to create a more fine-grained mapping or understanding of the space I'm looking at. So that's a lot of words. Let me try to give you an analogy here. So one example, and again, I really like this analogy of resolution, because it plays well into the analogy of using Google Maps, right? So, or Google Earth, Google Maps, or any kind of mapping software. Suppose you have Google Earth, and you start off, you have like America's here, North America, South America, whatever. My drawing skills are not the best, but you have an understanding of what's going on here. You have Asia and whatnot. This map is great for answering very broad questions. So answering questions about countries, answering questions about oceans, and large scale problems. This is all you need. You just need this map, right? But the moment you start asking more fine-grained questions about particular cities, for example, like if I ask you a question, about Waterloo here, then it's hard because you don't have enough resolution on this map in order to be able to answer this question. So you zoom in, you zoom in, and then you have a map of Waterloo, which I'm not going to draw out, unfortunately, but maybe, you have different roads and different streets, and then you have, some river that, goes this way and then splits off that way. So now you have the representational capacity or the, modeling capacity in order to be able to answer more fine-grained questions about this particular city of Waterloo. And that's really what it's all about, is our idea is we're going to take machine learning models and try to apply this analogy, or not apply this analogy, but try to create a more high resolution understanding of particular concepts when we need to. So I really like this analogy, just Google Earth analogy. I think it's very powerful, and it's a great way to kind of intuitively understand what we're trying to do in terms of machine learning. To kind of extend this analogy a little bit, notice that when we have this fine-grained map, we don't really care about what's happening around it. So once we've zoomed into Waterloo, we can kind of ignore everything else. This is all we care about, and so we don't care too much about the resolution or the quality that's lost in other parts of the world. We really care about what's lost or what's gained near the Waterloo region. By the way, for those who don't know, Waterloo is just a small city in Canada, and I just happen to live there. But this kind of concept that we don't need to preserve any information about other parts of the world, we just care about this part that we're zooming into, is also something that I think extends to this machine learning concept. So this is kind of my understanding or my presentation of the problem that we're trying to solve. And I'm going to slowly get into how we're aiming to solve this. And I'll start by talking a little bit about a recent research paper, quite a famous one by Google called Titans. So I think the exact title is Titans, Learning to Memorize at Test Time. I don't have the paper here loaded in this notebook, so I'm just going to go off of my understanding and kind of what I can remember from the paper and the idea that they present and how it relates to what I've presented so far. Titans essentially aims to solve this problem of zooming in and not having enough resolution in a very particular way. And what they say, and by the way, if you haven't looked at the Titans paper or the architecture, I highly recommend looking at Umar Jamal's video on this, because he has incredible machine learning videos, and I think his explanation of Titan and his walkthrough of the paper is quite incredible and gives you an intuitive understanding of what's happening. But just to give you a brief about what Titans is trying to do, it looks at models where you have your input layer, and you have two parts to this machine learning model. You have an RNN that goes right here, and usually these models are for sequence modeling, the models that you'd apply this Titans paper to. So you have an RNN. And the goal of this RNN is to kind of compress the sequence. But we don't want to use a VAE or any other encoding. I mean, all of these are already encoded. Embedding space. So you pass this through an embedder, and et cetera, et cetera. But we don't want to use an encoder here, because we want to model sequences, and so the paper talks about using an RNN, and then after that you have your transformer, and this could be a series of transformer blocks, whatever, and then you have your output. So the important part here in these kinds of ensemble architectures is during training, whatever inputs you pass into this input layer, and in fact, I'll make a copy of this architecture because I'm going to draw all over this and kind of create a mess. Whatever inputs you pass through here, through your RNN at training time, these are the sequences that your model is going to learn to compress effectively. So essentially what's happening here is you pass a sequence in, and after it gets embedded, et cetera, you pass it through this RNN for compressed sequence modeling. So it tries to model the sequence, which might be pretty big, and make it pretty small. So we're able to efficiently use transformer afterwards. And then this transformer, so this RNN learns to encode information, and then this transformer here learns to use encoded information for sequence modeling. So it kind of extracts info from the encoded information, encoded state. So during training time, this is what takes place. But suppose you pass an input into this model, and suppose it's a language model, and you pass it a prompt that it's never seen before. So some like anomalous or out of distribution prompt. So things that the model has not seen before. We call these out of distribution. So you pass it some kind of out of distribution prompt. And so, the embedding model is fixed. This is fine. It's able to encode the information. But when we get to this RNN, it's never seen data like this before. It's never seen a sequence or a prompt like this before. So this RNN kind of fails at its task of encoding this information further. And therefore, it's not able to kind of retain as much information in this encoding as it needs to. There's a loss of important information when this prompt is out of distribution. And then in this transformer layer, because there's not enough important information encoded by the RNN, this transformer does not know what the important information to extract was, because there is just none, right? So this entire architecture kind of just fails, and it starts to hallucinate, and the performance on out of distribution prompts is pretty bad. And I guess one way of thinking about this is, in our data set, one assumption that we have is our data set is so big that there is no prompt that is far out of distribution, right? So if this was our entire data set, was just cats and physics, then we're basically saying there's no prompt that's all the way out here. This prompt is so far out of distribution that it's no longer natural language. We're assuming that our entire data set is natural language. So this data set that we're training on is all of, like, pretty much all of natural language. So if there's something that's out of distribution, completely out of distribution, it's no longer natural language. So this wouldn't even make sense to a human. So our assumption is out of distribution data sets lie within, somewhere within our data set, out of distribution data points lay within some distance of our data set. So they're not too far out of distribution, but the model hasn't learned to generalize or build a good enough understanding of these set of data points, or, these out of distribution set of data points. So what the paper suggests is, instead of just having this RNN here, let's also train a separate thing called neural memory. And, well, they call it neural memory, but it really is just a linear layer. So, this is just a linear layer, a matrix multiplication, some activation function. And this neural memory is on the fly going to learn a good compression for this input information. So this is trained anytime there is an input that is seemingly out of distribution. So this neural memory is trained at test time, and that's kind of what in the Titans paper they deem test time training is. Let's introduce this separate network that isn't connected directly to our base model, and let's train this on the fly to be able to kind of do the task of the RNN, because we don't want to train the entire RNN on the fly. It's too big. So we train this one layer to do the task of the RNN just for this particular prompt, and maybe a small data set of similar prompts that we might have. So it's trained at test time on the prompt, and the loss here, for example, would be a reconstruction loss. So just how good is this layer able to take this prompt, compress it, and then decompress it, or expand it. So the idea, and I'm not going to go into how they do this because I don't have a great understanding of how they do it either, because they haven't released their code. But this, or at least, to my knowledge, they haven't. But this neural memory, it acts like the RNN, and then this is used with the transformer, or maybe with the RNN, to kind of improve the encoding of this particular piece of information that might be an out-of-distribution sample, by continuously training at test time on this sample. So this is kind of the Titans architecture, and this is why they call it learning to memorize at test time, because that's really what they're trying to do, is they're trying to create an external network that on the fly is able to train and memorize an encoding for the prompt that's given. So this idea, and also once you use this prompt, we can reset this neural memory after use, because we don't really care about generalizing this neural memory to other prompts. So that's the idea here. It's kind of like the Google Maps idea, where when you zoom into a particular location that you're interested in, you don't care so much about the other information anymore. And once you zoom back out, you can forget that. So we only when we train this neural memory, we only care about the prompt that's provided in this instance, in this inference instance, and we only train on that and maybe some similar samples, and I'll get more into that later. And once we're done with this prompt, and once we've created a prediction that we're happy with, quote unquote happy with, then we can reset this neural memory and we don't care about it anymore. So this is how Google, in their Titans paper, present test time training. Now, what we want to be able to do is, this is a very particular use case, right? So we want to be able to generalize this kind of test time training paradigm to other models and use it in other circumstances. So now I'm going to step back and take a more theoretical approach again. And so let's get our data set back. So let me just copy a small portion of this mess over here. Let's say this information. Actually, let's keep these as well. Just keep this information here and just copy it down. So this was our data set, and this was our problem. And now we want to generalize this idea of test time memorization, or test time training, actually, to be able to work on different types of out-of-distribution samples. So what we want to do is we want to do something very similar to this. But instead of just using neural memory to improve the encoding process of an RNN that's one part of this ensemble model, we want to be able to use test time training on any model when it sees an out-of-distribution sample in, let's say, natural language processing, right? So we want generalized test time training. And I'm not going to talk about how to implement this or any architectures involved, but I'm going to give a more intuitive understanding as to what this looks like and how this might play out. So we want generalized test time training. And that's going to be very similar to our Google Maps analogy from here, which I will also copy. In the sense that we have this data set. Let me move this data set just over here to the right. We have this data set, and we have a model that's able to create a low resolution representation, or have a low resolution understanding of this data set, right? And so our model is kind of smooth in some sense, and I'll draw this two-dimensionally as some model data fitting problem. So our data set might look something like this, and we see we can fit some kind of model here. So maybe there's more dense data here, so we can form a more robust understanding, more dense data here. And so our model might look something like this, where it's able to fit the data set, but it's not able to really fit the fine grain resolution or fine grain frequency. And typically this is good, because when a model fits to every single data point, so instead of having this, if I had a model that did this and tried to just interplay between every single data point, this can cause a lot of issues when it comes to generalizability, because you might have a fit where, for example, down here it goes all the way down, fits this data point, and all of a sudden this understanding in this region is non-generalizable understanding, right? So typically we want to keep our model smooth in its approximation of our data set. And this is true in general for most, statistical modeling problems. But now suppose we kind of zoom into this portion of our data set, so this kind of high density portion, and let's say this density portion it pertains to cats. We zoom into this and we really have a closer look at it, and we notice that there's even finer grained patterns. So notice how our model kind of models the section like this in some sense, and in this kind of shape over here. But maybe our data set has more fine grained patterns, more fine grained frequencies that are built into this kind of data, right? So on average, our model is great on the entire corpus of human data. It's good at modeling our data, because remember, it has to model all of human knowledge. So at a low resolution standpoint, it's able to model what we need for most tasks. But suppose now you have, again, maybe a distinction between domestic cats. So here maybe you have domestic, versus over here maybe you're talking about wild cats, right? So these data distributions look more nuanced, and so maybe what you'd really like is to have a model that's able to fit this distribution more closely. Actually, I'll draw this in a different color. I don't want to use red again. Let's say orange. So really what you'd want is to be able to have a model that's able to fit this distribution more nicely. And maybe, you scale your red model and you get an orange model that's able to fit this distribution. Well, then you can zoom in further into the wild portion, and maybe then your model kind of has this shape, but the data distribution, although it has the shape you're looking for, it still has more nuance that you haven't been able to map properly. So within this data distribution, you have maybe lions versus tigers versus jaguars. So maybe you have subspecies of cats, of wild cats, right? So maybe this is like lions, tigers, etc. And you want to model this better, so you go and you scale your model up again, and so you get this green model, which is able to really model this high resolution data. And remember, this high resolution data exists everywhere across our data set. It's for every single topic. It's for every single proper noun. It's for every single abstract concept in every single field. Is a huge amount of resolution. And we cannot fit this resolution in billions of parameters. So, and scaling is not going to be our solution. So this is the problem we're trying to solve. It's a problem where we don't want to overfit to our data set in places where we don't need to. So we need the model to be smooth. So we need smoothness, but we also need nuance in order to be able to answer more complicated questions. So again, most models are fine when it comes to answering questions about subspecies of cats, of wild cats. But when you start asking them unseen problems in physics, or unsolved problems in physics, it's not able to have that high resolution understanding of what it needs to do. Maybe you give it a programming question, and it hasn't seen something quite exactly like that problem before, so it hasn't fit to that particular data point, or maybe the problem is so in depth that it hasn't been able to model that resolution that it needs. Anyways, this is the problem we're trying to solve, is a problem of resolution. And so our kind of solution or workaround with test time training is, instead of scaling the model in order to go from the red to the orange model in here, in this example here, let me get the pointer back. So in this example here, scaling the model can get us from red to orange, but we don't want that, because our models are going to just become huge, and at some point, we're going to hit a computation limit, a size limit, and then these models can be used, on edge devices, etc., etc. So we don't want this. So instead, what we're going to do is, suppose our model, originally the red model, looks something like this. So this is our model, and our model has been given a prompt that it's not able to understand perfectly, right? So maybe this is a sample or prompt, and it's out of distribution. What we might want to do, and remember, our data set is very dense, so there might be other prompts as well nearby that the model has seen in our data set. So maybe I'll make this red, and these are things that are from our our data set, our training data set. But the model just doesn't have the representational capacity to be able to model these fine-grained details for this particular topic. What we're going to do is we're going to take this set of similar data points. Maybe they talk about similar topics, or maybe related concepts of whatever the prompt's about, and we're going to train the model on the fly. And this is really what we want when we talk about test time training, is we want to train the model on the fly to be able to better fit this data in order to better be able to answer this prompt. So maybe you train it a little bit and it gets a little bit closer, a bit better, and then you train it a bit more and it gets a bit better, even more. And then eventually it gets to a point where it's really good at modeling this fine grain resolution in the data set. And now this fine-tuned or this trained model, this retrained model, is able to answer the question the way you want to, understand the question the way you want it to. This is the problem we're trying to solve, and this is how we're going to solve it. Something I haven't spoken about here, which is a big bottleneck in this area of research, is when you're given a sample prompt, the first thing you have to do is to identify that this is out of distribution. Because you don't need to train on things that you could have answered from the global resolution. So again, if you're answering things about countries, oceans, etc., you don't have to zoom in on Google Earth. So the first thing is you need to identify when your prompt is out of distribution. The second thing is, I spoke here about maybe having similar data points from your data set. That's a big question, is how to get training data at test time. Because in Google's paper of Titans, our training data is just the prompt itself, because we only care about encoding the prompt, and we can use reconstruction loss. So this can be done in a completely kind of self-supervised manner. We don't need a labeled data set in this case. But in this instance, you are trying to generalize beyond just encoding ability into understanding ability. And for many training tasks in language modeling, you might need a labeled data set for this. So the second problem is, how do you get your training data at test time? How do you do this? So these are kind of two of the big constraints. Of course, the third constraint is what do we train? Which, of course, you're not going to train your entire language model. You might be training a particular set of layers. You might be fine-tuning using LoRa, or whatever. But that's the third question here is, how are you like what exactly are you training, and how are you doing it? I think the most interesting part here is understanding how to get your training data at test time. And I'll talk about this briefly. And I think I'll keep the next application of test time training to a separate video, because this video is getting pretty long. But really, our question is, how do we get good sets of training data such that our model is actually able to turn into this orange model that we want, and is actually able to model our data better? Because we don't just want to train on our sample prompt anymore. And maybe we aren't able to train on our sample prompt because we need labeled data, right? So our sample prompt might not even be in our training data set, and it likely shouldn't be in our training data set. So traditionally, people have been just using k nearest neighbors in the embedding space. And this does not work. And the reason k nearest neighbors does not work is, suppose your prompt in your embedding space. So now I'll kind of draw the embedding space a little bit. So say this here is your embedding space. It's some rk, you know, and r like rd, because we're using k for k nearest neighbors. And your prompt is here, and actually your prompt is in red. Prompt is here. Your prompt. And suppose a prompt is asking you information about cats and physics, and it's some information that's in between cats and physics. So it might ask you about why cats in particular were used in, you know, by Schrödinger for his experiments or whatever, right? So suppose your model hasn't looked at this data before. It hasn't, you know, trained on those particular examples, but it sees cats, and it sees cats over here. So this is a bunch of cat stuff, and then it sees physics, and it sees physics over here. So here's cats. Here's physics. And you run k nearest neighbors on this, and if you can't already tell the problem, yes, we have a cats cluster. Yes, we have a physics cluster. But the cats cluster is slightly closer to the prompt than the physics cluster is. And therefore, all of your k neighbors chosen are going to be somewhere here, right? So they're all going to be cat-related prompts. So you only get cat-related information. Related data. And you get nothing related to physics, and you might end up fine-tuning on the wrong thing at test time. So k nearest neighbors, it's naive, and it's quick, but it's not going to suffice for us, right? We need to be able to train on things that are kind of here as well as here, because, like, remember, if we're training on things that we're trying to answer a prompt that's about cats and physics, and if we only train on cats, then we might lose resolution on the physics side. So that's another thing, is when you train these models, you have this orange retrain model. When you train these models, you can lose resolution downstream on other tasks. So now let me give you a more holistic picture of what's going on. So you have to identify that this prompt is out of distribution. You get the data at test time. So here, you identify the prompt is out of distribution. You get the data at test time, and then you start training, and then you answer the prompt. You run inference, and very similar to neural memory, this new fine-tuned model is going to be very good at answering questions for this particular task, but it's going to be very bad at answering questions. It could be very bad at answering questions for other tasks now, because you fine-tuned, you might lose information that you had stored, or you lose parameters that store particular information for other tasks. So once you're done with inference for this particular set of concepts, or this particular set of topics that you're done asking the model about, you reset the model. you go back to your original base red model, and that ensures that you're not losing resolution in other topics. So a good example of this is you might want a model that's particularly good at coding and is only used for coding tasks. And so you might train a base model that's very good at general language understanding. Then you might train a model that's good at coding. And this is just done using regular fine-tuning. But the further, suppose your GitHub repository or your code base gets from the training distribution, the further it gets from this training, the harder the model is going to have, or the harder of a time the model is going to have modeling even that information. So that's almost like coding is Waterloo, and then I ask it particular information about particular code or about particular paradigms or particular design choices, and maybe the model does not have the resolution to answer that. So maybe that's a very, very small part of your Google Maps or your Google Earth space. So then you have to start fine-tuning, and you do this test time training, but realize this model is not going to be able to answer any general questions anymore. It'll lose information in other parts, right? And again, in the Google Maps analogy, you don't care about information in the other parts. So once you're done running inference on this particular set of examples, then you reset the model, or you go back to your base model, and you don't care about the original or the test time trained model anymore. That's something important to consider. But when you're looking for these data samples, you want your model to have the capability to answer this while not losing information on this, right? So you don't want to lose information on this space. And so you need some samples from this space. Use my pointer. You need samples from here near physics in order to retain information about physics. When you're fine-tuning, you don't lose resolution here, or you at least gain maybe gain some resolution here, and you need some samples here for vice versa. So k-nearest neighbors, it will choose. It can give you very, very similar options, but it'll give you a bunch of redundant information without getting you all of the necessary information. So really, one research question here is what works. So I'm gonna leave it at that. I'm not gonna talk more about data set searching, but that's one kind of limitation or one problem when it comes to test time training. I think I've spoken quite a bit about this paradigm of test time training, at least for the use in language models, and I think I will leave it at that for now. I'll put a PDF of these notes, although they're pretty messy, and I'll put those in the description. And yeah, this is mostly just for me to kind of document my journey through understanding machine learning and document certain ideas, because I know myself that over time, at the moment I might be very interested in test time training, but over time I will also lose resolution and understanding of these concepts as I become more interested in other things, or as I go deeper into other fields. So I kind of want to make this video to document my understanding and my ideas of test time training while I have them fresh in my head. And the entire video was completely unscripted. I don't have any script or anything. I'm just kind of drawing on my iPad and rambling from my memory and from my knowledge of what I know. And so yeah, that's about it. And next time, or I'll talk a bit more about a different use of test time training in a different video. I want to talk about how I could use test time training in my particular research, and that researches on wind super resolution models. So it's a completely different application of test time training because it's not for language understanding anymore. And it's a very interesting application of test time training because you have very, very interesting form of data which needs you to think about making these models in a completely different way. So you can't really use this generalized pre-training and then test time training approach. You need something that's a bit more nuanced to the data set that you're working with. Um, but yeah, I'll leave it at that for now. And I hope this covered um, a lot of intuitive, or I hope this presented a lot of intuitive information about test time training.